Hello, it's Scott Manley here. In the 1940s, the V-2 was the world's first large liquid-fueled rocket. Developed by German rocket scientists led by Wernher von Braun, it would be used as a weapon in the later stages of the war. Ultimately, it wouldn't change the course of the war, but it would have a massive influence on the years after the war. Scientists and engineers who had worked on the project would work with other countries to develop their rocket technologies. France, Britain, the Soviet Union, and of course the United States. In particular, von Braun took a great number of risks to ensure that he would surrender to US forces rather than the Soviet Union. And 25 years later, he was instrumental in helping the US land humans on the moon, realizing his childhood dream of space travel. But the first human to fly on a rocket which von Braun had a hand in was Alan Shepard on Mercury Redstone 3, also known as Freedom 7. This rocket would have a great deal of heritage in common with the V2, but I haven't really done a story about how we went from the V2 to the Mercury Redstone, and how the rocket engines that were designed for the V2 evolved into the engines on the Redstone and formed the basis for the engines on Atlas, Thor, and Titan. So the V2 was powered by the Model 39 rocket engine, and it was a 1-ton engine that generated 25 tons of thrust, and the propellants used were liquid oxygen and alcohol, specifically 75% ethanol, 25% water, and this meant that you could literally drink this rocket fuel, and actually lots of people did apparently. But even the thirstiest brigade of soldiers couldn't keep up with the engine, which had to consume over 100 litres of alcohol per second. To feed all this into the rocket, they had a pump system which was driven by a hydrogen peroxide gas generator. And that's distinct from most modern rocket engines which use the regular fuel and oxidizer supply to generate the power for their pumps, meaning that you don't need to load a third propellant to make it work. So the alcohol and the liquid oxygen get injected into the top of the engine through these burner cups, and this is something that is very different from the injectors that are found on modern rocket engines. The V2 developers were pioneers in rocket science, and they hadn't figured out all the modern tricks for how to mix propellants, how to mix the oxidizer and the fuel, so that when they burned, they did so in a stable manner and didn't cause combustion instability. And the design that they used were these little combustion cups or baskets. You had liquid oxygen getting sprayed in through that head in the middle, and around the outside they had these little swirly vents that would spray in the alcohol. And while this worked, it was really laborious to produce these little vents on the side. Those were all individually machined brass pieces of hardware which were screwed into this larger cup. And in turn, there were 18 of these on each engine, so that was a lot of hand labour to manufacture all this. And in turn, each of these cups would require, plumbing for the oxidizer to come in, so it vastly increased the complexity of the engine, but this is what they had. One way to think about it is each of these cups is like a mini combustion chamber feeding into the main combustion chamber, and each of them generates just under 1.5 tons of thrust, so in total it has a bit over 25 tons of thrust from 18 of these. Now, a scientist called Walter Thiel, who was the expert in combustion, he had actually designed a version with a single large injector at the top, and they had been trying to test this and solve the problems, but in 1943 he was killed in an air raid, and so this improvement never made it into an actual rocket. Now, this design also features a single inlet on the cooling manifold down on the nozzle. And if you compare that to the production version, they had multiple pipes leading into this carrying the cooling alcohol, and that obviously increased the complexity of the engine. This change was patented by a guy called Konrad Dannenberg, in the late war, but by that point it was too late to actually make any changes to the production, and this would only come in after the war. So I want to be clear that Project Paperclip didn't just bring a bunch of hardware and a bunch of engineers who'd built it. They also brought the ideas they had to improve on it. So the US changed the name of the V2 back to the A4, and they began using it as a large sounding rocket. And in 1946, they got the first footage of the Earth from space. They also attached solid rockets to the top for the bumper project, reaching even higher altitudes. But the real technological development on the engines would be on the Navajo missile. The Navajo was a project by the newly created Air Force. It was a cruise missile which would be launched under rocket power, and it would ultimately fly on ramjets, thousands of miles to its target. So the initial requirements for this were laid out in late 1945 by the US Army Air Force. It was designated MX-770, and it would have a range of 500 miles. The first contracts for this were awarded in 1946 to North American Aviation, who of course had been building a lot of aircraft during the war, and now, having stood down a lot of their production capacity, were looking for new things that were needed built, and they had very specifically set up a rocket team for this eventuality. They were supplied with 2 Model 39 engines which had been recovered from Germany, and the first thing they did was they tore them down, took them all apart, catalogued every single part, figured out how it was built, and then reassembled them and test fired those engines. Those were their Mark I engines. The next step was to figure out how to build them using US capabilities, and one of the problems was that Germany had of course used metric, and the US was using, the imperial unit system derived from, feet and inches and pounds and everything. So as well as changing all the measurements, they used new bolts, new O-rings, all sorts of other materials had to be adapted, and this would be the Mark II. Now, it wasn't an exact copy. The image on the left, I believe, is of a Mark II engine. And if you compare it to the original on the right, first of all, look up the top. You'll see that the truss structure is very different. The turbo pump, the plumbing, all that is shifted around, and the whole thing is a whole lot shorter, even when you account for the fact you have to add the peroxide tank. But before the Mark II was actually finished, they got access to the Model 39A with the single injector plate. And knowing that if they could make this work, it would be better in almost every way, they focused their energies on that, while they kept the Mark II work on in parallel for experience purposes. Another critical thing that happened around this time was that the US Army Air Force was disbanded, and instead the US Air Force stood up. And for political reasons, there was a demarcation in what the missile responsibilities were. Missiles with less than 1,000-mile range were the Army's, and missile more than 1,000 were going to be the US Air Force. So they actually expanded or increased the capabilities of the requirements for the Navajo missile to make sure that it was an Air Force project rather than an Army project. This also meant, by the way, that von Braun's team wouldn't actually be involved directly because they were with the US Army, and this was now an Air Force project. Increasing the range requirements also increased the mass at launch, which meant they had more powerful engines, and the Air Force now required engines with a thrust of 75,000 pounds, or about 34 tons. So the Mark III was built with this in mind. It became the XLR-43. They solved the combustion instability problems, presumably because they had more time and money. And that also let them simplify the combustion chamber, making it cylindrical rather than spherical. They developed new manufacturing techniques for the liquid-cooled combustion chamber. And so this engine, which had begun as the Model 39 for the V2 built by German scientists, had been evolved and optimized by American engineers. It would later be taken up by von Braun when he was designing the Redstone rocket in the early 1950s. And so after a few more iterations, test flights, it would ultimately be called the Rocketdyne 75-110 A7. It still used the same propellants, alcohol, liquid oxygen, hydrogen peroxide, but now it generated 37 tons of thrust. It had higher specific impulse, higher chamber pressure. It was half the weight and significantly more compact. In addition to the monolithic showerhead injector and the redesigned combustion chamber, they had improved the turbopump. They had a much better steam generator. And of course, the redesign had massively reduced the part count and the labour that was required to build these engines. And so, as I said, this engine would launch America's first satellite. It would launch America's first astronaut. Now, there were some changes to make this happen. First of all, for the first satellite, Explorer 1, they replaced the propellant with something a bit more energetic. It was something called Hydyne, a mixture of UDMH and diethylene triamine. This was great, it gave them a bit more performance, but it was sort of toxic. So when they went to launch Alan Shepard, they switched back to using alcohol, and by that point they'd also stretched the tanks a little on the Redstone, and they needed to add a bit more hydrogen peroxide to the engine to let it, operate for the full duration. But I love the fact that America's first astronaut was launched into space using the equivalent of very strong vodka. But while this launched a couple of important missions, the V2 engine's heritage within the US space program was assured by a different route. So the Navajo missiles' capabilities had kept on growing. They were now looking at needing a pair of 120,000 pound thrust engines. That's about 55 tons of thrust each. So they developed new and bigger engines based on what they'd learned. Taking everything they'd learned from the German engine designs, they started again and they developed an engine called the XLR-71. And in addition to being more powerful, the big innovation came from getting rid of the steam generator system. There was no longer any need for hydrogen peroxide because instead they would have a gas generator that would use the oxidizer and the fuel to generate the gas. They were also switching the fuel over to be something like 92% alcohol, which made it a little more energy dense, a little harder to cool, of course. Two of these would be adapted together to form a single unit, generating 240,000 pounds of thrust. But the Navajo kept getting bigger, and the third version required over 400,000 pounds of thrust to get off the ground. So they switched fuel types over to kerosene and liquid oxygen, and they added a third combustion chamber to get the necessary thrust. But by the time the third iteration of the Navajo cruise missile was being tested, it was very clearly old technology. Ballistic missiles, using the technology that Rocketdyne had developed, were now able to cross similar distances much faster. The engines used on the Atlas, the Thor, the Jupiter, even the Saturn 1B, they were all related to the engines that had been developed by Rocketdyne for the Navajo. Since ICBMs were able to cross the distances faster, the Navajo was no longer needed and it never reached deployment. But engines related to the LR-79 kept flying right up until 2018 with the last flight of the Delta II. And of course, if you look across to the other side of the world, Russia is still flying the Soyuz, which is derived from the R-7, which we know those engines have some well-documented heritage based on the Soviet version of Project Paperclip, Operation Osavaikum. I think I've mispronounced that, but that really is a story for another video. I'm Scott Manley. Fly safe.